Hello, my name is Fred Ernest. Welcome to this brief introduction video on EMC and signal integrity. I am a results-driven INARTI certified EMC engineer with over 40 years of experience in EMC compliance, product safety, Wi-Fi 802.11, telecom and RF design and testing across consumer electronics, automotive and aerospace industries. My expertise spans global regulatory compliance, FCC, CE, MAL STD, DO-160, EMC testing and design. This includes RF shielding, PCB layout optimization, and engineering process optimization. As the founder and principal consultant of Ernest Consulting, I bring my decades of expertise to help companies achieve compliance, mitigate EMI challenges, and accelerate product development. In this video, we'll explore key principles of EMC and signal integrity, uncovering common challenges and best practices to ensure robust, compliant designs. Let's dive in. Electromagnetic compatibility, or EMC, is often perceived as a complex subject, but its fundamental principles are surprisingly intuitive. EMC ensures electronic devices coexist without interfering with each other. This is achieved by minimizing emissions and ensuring immunity to external interference. EMI can be radiated through the air or conducted through cables. Poor EMC design can lead to device malfunctions and safety hazards. Effective EMC design minimizes EMI and ensures device resilience. While EMC focuses on a broader electromagnetic environment, signal integrity zooms in on the fidelity of electrical signals within the PCB itself. Ensuring data arrives without distortion is crucial to avoid system malfunctions. Impedance represents the resistance a signal encounters as it propagates along a conductor. Mismatched impedance causes reflections, distorting the original signal. Techniques like impedance matching and controlled trace routing help maintain signal fidelity. Section 4. Common PCB design issues: grounding, crosstalk, and power integrity. In PCB design, minor oversights can lead to significant EMC and SI problems. Common issues include poor grounding, crosstalk, and power integrity problems. Grounding forms the foundation of a stable PCB. Poor ground planes can lead to high impedance and ground loops. This can cause EMI issues. Crosstalk occurs when signals on adjacent traces interfere. Power integrity issues arise from noise on power supply rails. Section 5. Best practices for achieving EMC and signal integrity. Mastering EMC and SI in PCB design requires a proactive approach, employing best practices to mitigate potential problems. A solid ground plane is essential for good EMC and SI design. It provides a low impedance path for return currents, reducing EMI. Minimize trace lengths to reduce resistance and inductance. Use controlled impedance routing for high-speed signals. Place decoupling capacitors close to IC pins to suppress noise. Gap 3s. Section 6 CST Studio Suite EMI Simulation Tutorial. Utilizing advanced simulation tools can be a game changer in achieving optimal EMC and signal integrity in PCB design. One such powerful tool is CST Studio Suite, which offers comprehensive electromagnetic simulation capabilities. Let's walk through a basic tutorial on using CST Studio Suite for EMI simulation. Open CST Studio Suite and start a new project. Select PCB Design from the project templates. Import your PCB layout files. Set up the simulation parameters. Define the frequency range of interest. Configure the boundary conditions. With the setup complete, run the simulation. CST Studio Suite will analyze the electromagnetic fields and currents. Pay attention to hotspots and regions where signal integrity may be compromised. Review the results and generate a report. The report will include detailed insights into the EMI performance of your PCB. By leveraging CST Studio Suite, designers can address potential issues before physical prototyping. This tool enables a deeper understanding of the electromagnetic behavior of your PCB. Stay tuned as we move on to real-world PCB analysis and improvement in the next section. Section 6, Real-World PCB Analysis and Improvement. Let's analyze a real-world PCB layout and identify areas for improvement. Consider a hypothetical two-layer PCB for a data acquisition system. The top layer contains the components and signal traces, while the bottom layer serves as a ground plane. Upon inspection, several potential issues become apparent. The ground plane is fragmented, increasing ground impedance and creating potential ground loops. High-speed data lines run in parallel without shielding, making them susceptible to crosstalk. To address these issues, implement a solid ground plane, reroute high-speed traces, and review decoupling capacitor placement. These modifications will significantly improve the EMC and SI performance of this PCB. Conclusion: designing for success in the electromagnetic environment. Mastering EMC and SI is essential for successful PCB design. Ignoring these principles can lead to significant problems. Adhere to best practices to create functional and resilient PCBs. A solid ground plane is crucial for good EMC and SI design. Employ controlled impedance routing for high-speed signals. Carefully consider component placement to minimize noise. Learn from real-world examples to improve PCB designs.